Chapter 5: Topological Aspects of Numeric Emergence and the Geometry of Differentiation. The emergence of number from the supersymmetric zero state is not only an algebraic or probabilistic phenomenon, it is, at its core, deeply geometric and topological. To fully grasp the mechanisms and constraints of numeric differentiation, we must analyze the manifold structure of the state space in which these processes occur. By doing so, we uncover how the geometry of this space encodes essential information about both the accessibility of different numeric configurations and the allowed transitions between them. The topological perspective is crucial for understanding why the zero state is so fundamentally unique within the universe of possible numeric states, and how its special properties enable the observable contrast of numeric values to be generated through mathematically well-defined geometric operations. Let us begin with the state space itself. The collection of all normalized quantum states formed from our infinite-dimensional Hilbert space, denoted H sub n, naturally forms what mathematicians call a complex projective space of infinite dimension, written as CP infinity. In this space, states that differ only by an overall complex phase factor are identified as representing the same physical configuration. That is, multiplying any state by a global phase does not alter its measurable properties, and so all such states are considered equivalent. This complex projective space is not merely an abstract mathematical construction. It is the natural geometric setting for all quantum states, numeric or otherwise. This projective space is endowed with a profound geometric structure, characterized by the Fubini study metric. This metric determines the natural notion of distance between 2 points, meaning between 2 quantum states, in this high-dimensional space. The line element, which expresses infinitesimal distance squared, is given as follows: the inner product of the infinitesimal displacement d psi with itself, minus the squared magnitude of the inner product of psi with d psi. In practical language, this metric tells us how far apart 2 normalized quantum states are, taking into account the projective identification of global phases. The zero state, which we have denoted as ket z, holds a singular position within this geometric landscape. It sits at the point of maximum symmetry. At this location, all possible tangent directions, meaning all infinitesimal ways to move away from the zero state within the projective space, are equivalent under the action of the symmetric group on an infinite number of elements. This group, which permutes the numeric labels associated with the basis states, leaves the zero state invariant, making it the unique fixed point and the natural origin for all coordinate systems on the manifold. The analogy is much like the north pole of a sphere under stereographic projection. All directions from the pole are geometrically equivalent, and every path away from the pole can be understood as a geodesic, or the shortest path, within the curved space. To see the significance of this, consider the geodesic structure of the manifold. Geodesics, those are the straightest possible paths in curved space, emanating from the zero state, represent the most efficient or minimal routes for transforming the perfectly symmetric configuration into specific numeric outcomes. The process of numeric differentiation, therefore, corresponds to movement along these geodesics, starting from the origin of maximal symmetry and moving toward points of increasing differentiation and specificity. Collapse operators, which we previously defined algebraically, now acquire a geometric interpretation. Each collapse operator, corresponding to a particular number n, can be seen as a projection that maps the zero state onto a lower dimensional submanifold. This submanifold represents all states where the numeric value n is privileged or singled out. Geometrically, this is akin to projecting a point from a high-dimensional origin onto a lower-dimensional subspace. Each such operation traces out a fiber in the state space, with the base of the fiber corresponding to the possible numeric outcomes and the fibers themselves accounting for the remaining freedom in phases and amplitudes. The zero state, therefore, lies at the intersection of all fibers. It is the unique configuration that maintains symmetric access to all possible numeric outcomes through the appropriate choice of projection. This property, visible only in the geometric and topological analysis, underscores the universal generative potential of the zero state and explains its centrality to all processes of numeric emergence. When we turn to the topology of the state space, several remarkable features emerge. First, the fundamental group of the complex projective space, denoted pi1 of Cp infinity, is trivial. This means that any closed path in the state space, any loop, can be continuously shrunk to a point. This property is called simple connectivity and implies the absence of topological obstacles to continuous deformations within the space. However, the higher homotopy groups are not trivial. In particular, the second homotopy group, denoted pi2, is isomorphic to the group of integers. This means there exist non-contractible two-dimensional surfaces, topologically protected features that cannot be continuously erased. These invariants are crucial. They underlie the stability properties of certain numeric configurations and restrict the possible ways in which the system can transition between states through continuous processes. The cohomology ring of the complex projective space provides yet another layer of structure. It is generated by a single fundamental class called H, which resides in the second cohomology group with integer coefficients. All higher cohomology groups are generated as integer powers of H. In spoken mathematics, the entire cohomology ring is isomorphic to the ring of polynomials in H with integer coefficients. This algebraic structure encodes global topological data about the state space and provides powerful constraints on how numeric differentiation processes may unfold or be reversed in terms of allowed geometric transitions. Of all points in the state space, the zero state is topologically unique. It is the only fixed point under the full group of permutations acting on the numeric labels. This means it is the center of symmetry for the entire configuration space. All other states can be generated by moving away from the zero state through some combination of geometric operations, but only the zero state remains unchanged under all possible relabelings. The group orbit structure, which tracks how states transform under permutations, identifies the zero state as the sole representative of the trivial orbit, one that is invariant under every element of the group. This allows us to introduce the concept of numeric complexity, a geometric measure of how differentiated a given state is compared to the maximally symmetric zero state. This complexity is naturally defined using the Fubini study distance, which, between any normalized state psi and the zero state, is given by the arcosine of the absolute value of their inner product. In other words, the complexity is the angle in Hilbert space between psi and z. Completely collapsed states, such as pure numeric eigenstates, achieve the maximum possible distance from the zero state. The more differentiated a state is, the farther it lies from the origin in this geometric sense. The level sets of this distance function, meaning the collections of states at constant Fubini study distance from the zero state, form concentric shells around the origin. Each shell corresponds to a constant degree of numeric complexity, offering a geometric classification of how resolved a state is relative to perfect symmetry. The gradient flow of this complexity function defines natural dynamics on the state space. This flow describes the way that numeric states evolve under processes of differentiation, such as collapse or measurement. The zero state itself is a saddle point for this flow. It is unstable under generic perturbations, tending to evolve rapidly toward more differentiated configurations, but it can be accessed from any other state by running the flow in reverse, essentially reconstructing perfect symmetry by undoing differentiation. This geometric and topological analysis reveals, at a fundamental level, why the zero state is both the unique and necessary origin of all numeric emergence. Its position at the center of symmetry, its accessibility through all geodesic paths, its invariance under permutations, and its topological protection through cohomology and higher homotopy groups collectively establish it as the only configuration from which all numeric structure can emerge, and to which all structure can, in principle, be reduced. The geometry of numeric differentiation is therefore not an incidental feature, but a deep consequence of the topology and symmetry of the quantum state space itself.